Hello and welcome to this video on tests of group means. Specifically, we're starting today by talking about the paired samples t-test. And before we get started with the paired samples, we will review quickly the one sample t-test and some of the features of that. And so we'll be looking at typically what a typical data entry looks like, and then also descriptive and inferential statistics for that type of test. And so I'm including it here so that you have a comparison to go by, so you can compare the one sample t-test and the paired samples t-test. So as a quick review, in statistics, what we do is we start with what we think of as our target population. And because we can't measure everybody, we take some kind of a representative sample of that population that we think represents them, and then we measure something. And in this particular case, we're measuring something that has sample mean, it has a sample standard deviation, and then what we want to be able to do is to infer a population parameter, such as the mean, the population mean, or the population standard deviation, or sigma. And for a one sample t-test, then the golden rule, and I have to review this just to make sure that everybody remembers this, the golden rule of data entry is that each individual is included on a separate line. And so if you imagine this is a data set spreadsheet such as Excel or SPSS, then each of these rows represents a different person, and that's going to be really important when we start looking at all different kinds of statistical tests. Here in the one sample t-test, you can't go too wrong. You just simply make a column of that, whatever it is that was measured, this continuous variable right here. Because we have a mean and a standard deviation, that tells us that this must be some kind of continuous variable that we're measuring. It can't be categorical. So that continuous variable in a one sample t-test is compared to some kind of reference value. I'll put reference, if I could spell, or some standard. Maybe it's reference to a previous time period, or it's a standard that you want to achieve. So it's compared to that particular thing, and this reference or standard is literally just a number. And so once we have entered all of these particular data points for each individual of that continuous variable, what we can do then is we can calculate descriptive statistics. And our descriptive statistics include pictures and numbers. Specifically, we would create a histogram of this variable right here. And dot 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 just simply means however many people are included. We would also calculate the sample mean and the sample standard deviation. The histogram lets us see the shape of that particular distribution. X bar tells us the location, and standard deviation tells us something about the spread. So those descriptive statistics give us a picture kind of collectively of that particular variable. I'm going to go back to an example that we've had before because this doesn't need to be new. In terms of the null and alternate hypotheses, we looked at an example where I think it was in one of the previous chapters where we were testing whether the average weight of individuals in a population was equal to 170 pounds. The alternate then would be that the average is not equal to 170. And our test then is a one sample, and in this case we're going to be calling it a t-test instead of a z-test, because we don't automatically know sigma. Remember that a z-test is only applicable if we have a known sigma value. The assumption here is normality, and I'm just going to write this with a capital N because that's the notation we've used in the past, and that is normality of the sampling distribution of the means. And so Remember, there are a variety of different ways that this can be achieved. One of them is that the underlying population is normally distributed with any sample size. But with the central limit theorem, this can also be achieved with smaller samples by not normal distributions, as long as your sample size is large enough. So the test statistic then here, we're going to include this as t is equal to x bar minus mu sub aught divided by, and again, we're assuming that we don't know the sample standard deviation, so we don't know the population standard deviation, so we're going to include the sample standard deviation divided by the square root of n. The sample that we used gave us an x bar of equal to 185. Here we're testing whether that is equal to 170, so that's what our subtraction is. Our standard deviation was 40, and that was divided by the square root of a sample size of 64. And if you remember, when we calculated that out before, we got a t value, or we got a z value of 3. This gives us the same calculated value of 3.0. And we then convert that test statistic to a p-value. Now, before we do that, we want to decide on a critical value below which we're going to say, well, we calculated a value here of 185. We know that that's different from 170. But is it statistically significantly different from 170? That's our statistics question when we're inferring something about the population. So our critical value of a p-value, we're going to say, is 0.05. If our calculated value is less than that, then we reject the null. If our calculated value is greater than or equal to the 0.05, then we fail to reject the null. Our calculated value of a t statistics here of 3.0 is p-value is equal, say p-value is equal to 0.005, and that is less than the 0.05. So that, just by itself, just that p-value would lead us to reject the null. Let's go ahead and look at estimation as well for this same exact question. If we were to think about a 95% confidence interval, that is equal to x bar plus or minus that t value times the standard deviation over square root of n. So we're seeing a lot of the same characters when we're calculating the 95% confidence interval. And the interesting thing then with t-values instead of z is they are dependent on sample size. If we have our degrees of freedom equal to 60, so we'll say df equal to 60, then t equals to 2.0, remember? So in this case, because we have a sample size of 64, our degrees of freedom are 63, which is pretty close to 60, so I'm going to go ahead and use 2.0 here. So here we have our 95% confidence interval is equal to 185 plus or minus 2.0 times this value, which is 40 over the square root of 64, which this quantity right here, 40 over 8, is equal to 5. So if we were to replace that, so that's 185 give or take 10. 2 times 5 is 10. 185 plus or minus 10. So that's a 95% confidence interval of 175 to 195. So in both of those cases, both by estimation and by p-value, we would come to the conclusion of rejecting the null. And so here I'll say reject the null. In other words, if we were to go back up here, we would say it is not reasonable that the average weight is equal to 170. If we were to say this in plain language, it is unlikely for a sample with a sample mean of 185 to have been randomly drawn from a population with a population mean of 170. In conclusion, if we were to morph this into the language of t-tests, the average weight of participants, mean 185, standard error equal to 5, was significantly greater than 170. And here you see the new terminology. We have t, so our t-value, and 63 is the degrees of freedom. Remember, the degrees of freedom is equal to n minus 1, so that's 64 minus 1 is equal to 63 in this case. And here's our t-value, and the p-value that goes with that is 0.05. As a quick review for our sample size, a lot of times this is one of the main questions that statisticians are asked is, what's my sample size? So the sample that we would need in order to detect this amount of difference can be calculated if we know the population standard deviation, which we don't usually, so we estimate that with the sample standard deviation, and the z of confidence, which is 1.96, and the z of power. If we were to say 80% power, the z value that goes with that is 0.84. So this would be our calculation. Usually we try to find whatever it is that standard deviation, and this is the value that we can manipulate. And so if we have a difference that is very small that we are trying to find, then what that does is it makes our sample size much larger. If on the other hand the difference that we're seeking is quite large, then the sample size that we need in order to detect that difference becomes smaller. You'll also see that there is a direct relationship between the standard deviation and sample size. So if the standard deviation goes down, the sample size goes down. If the standard deviation goes up or it gets wider, then the sample that's needed to detect that also goes up. The z for 95% confidence interval never changes, and the z for power of 80% never changes. You could theoretically change your power to 90% or 70%, and that would change this number right here, but 80% power is a pretty standard accepted level, and a 95% confidence interval with two tails is also pretty well accepted. So those numbers generally stay the same in the sample size calculation equation. So let's go ahead and look at what this same exact set of information looks like for a paired samples t-test. And the main reason that I want to show them here side by side is that I would like for you to see the similarities. Again, the golden rule is that each row represents a person. And then by person, that's kind of like a general way to say or unit of measure. So if we're measuring hospitals or if we're measuring countries, then each row represents a hospital or a country. But most of the time we're studying people, so each row represents a person or a unit of measure, whatever that is that we're measuring. Now, again, let's go back to the beginning where we're starting with a population. We take a representative sample of that population. We accurately measure something, and then we can infer back to the population parameter. In a paired samples t-test, the thing that we are measuring actually comes in a pair. So we have an X bar, and I'm going to call it A, and an X bar B. So we have 2 times that we're measuring something that's a mean. And the interesting thing about a paired samples t-test is, and this is the key, is that these 2 things within each person are related to each other. Each of those x bars then also has a standard deviation, A and B. And if we were to look at those within each person, this is what it looks like in the data entry part of that. Remember, each person represents a row. So each person is a row in the data set. Using the example that comes from your textbook, we were comparing something that is a continuous variable, LDL, while a person was eating cornflakes. And so I'm going to put corn here. And then they stopped eating cornflakes for a while, and then they ate oat bran for a couple of weeks, and we measured their LDL. So we would call this oat bran, or just plain oat for short. And remember, these are LDL measurements after the person has been eating that particular food for a given amount of time. The key here is that each individual ate both cornflakes and oat bran. So we're going to have some kind of LDL measurement at those 2 different time periods. Now they did, just as an explanation, they did what's called a crossover trial, which means that some of the people started out by eating oat bran and some of the people started out by eating cornflakes. And then partway through the trial, they stopped eating those things and started eating something else. And so they crossed over, so they are their own control. This is extremely powerful, because if we just took a bunch of people who were eating cornflakes and a bunch of other people who were eating oat bran, we wouldn't know if the difference was just because one group tended to have a higher LDL cholesterol than the other group. So it's very powerful to have this paired design, and a crossover trial is a typical way of doing that. And so if you think about this, instead of having descriptive statistics just of one variable, we're going to end up with descriptive statistics for both of these variables. We could have a histogram of cornflakes, we could have an X bar of cornflakes, we could have a standard deviation of cornflakes, and then we could also have a histogram of oat bran, and we could have a mean LDL cholesterol while they're eating oat bran, and we could have a standard deviation of their measurement while they're eating oat bran. Now the big important thing is that behind the scenes, without anybody knowing about it, what SPSS does, or any computer program that calculates this paired samples t-test, is it actually is using something called the difference score. And I'll call that diff here. So the difference for the first person between when they were eating cornflakes and oat flakes is going to be some number. And so we take one and literally just subtract the other one from it, and we're going to find this difference score. And each person, even though you can't see it in the data set itself, has this difference score. And the important thing about a paired samples t-test is we are really testing the difference. We are looking at a histogram of the difference. We are testing whether the average difference and the standard deviation difference are some particular thing. And so instead of focusing on the means and standard deviations and histograms of the individual variables that we measured at those 2 time periods that are paired within each given person, they have a pair, they're compared to their own self, we're looking at the difference between them. So here we have a histogram of the difference, and an X bar of the difference, and a standard deviation of the difference. And so our hypothesis is that the mean difference is equal to 0. And our alternate hypothesis is that the mean difference is not equal to 0. So was there a change? In other words, another way of saying this null hypothesis is there was no change. The alternate is there was a change. delta is change, was a change. And so we want to know, was there a difference between cornflakes and oat bran? And so that's what we're testing here. The test is a paired samples t-test, which is also known as the dependent t-test, because the difference, the before and after, if you were to consider one of these after, the oat bran is dependent on what that own person's individual sort of baseline when they're eating just regular cereal. That's dependent. So a dependent t-test is dependent on what their baseline would be with just regular cereal. So if they typically run at a certain amount and oat bran is somehow helpful, then we'll see a change for that person, but it's compared to where they started. And the interesting thing here is that the assumption for a paired sample t-test is exactly the same. Now, the only difference is that, remember, this is normality over here for an independent, for a one sample t-test. That is normality of the sampling distribution of means. This is normality of the sampling distribution of the X bar of the differences, and so that's here. So of that difference score, and so we're looking at the difference between the two things that we measured. The test statistic, I hope, looks very familiar to you, and I hope that as we go through here you're seeing that the one sample t-test and the paired samples t-test are very, very similar to each other. The test statistic t is equal to x bar minus mu sub 0 divided by the standard deviation over the square root of n. And somebody might ask, what on earth is the difference between that and this one over here? Well, the only difference is that this is the x bar of the difference. I wrote that really tiny small, but the x bar of the difference. And again, remember that because this is a t-test, this has a certain number of degrees of freedom, and that degrees of freedom is equal to n minus 1 here. Same exact thing, so no difference there. df equals n minus 1. We have to decide about a critical value. And so let's say we're gonna pick, let me go back to green, a p-value of less than 0.05. And if we were to run this analysis, we would get a variety of data that goes with this. So let me include this over here a little bit farther over on the right hand side. Actually, I need to write some of it up here. First of all, the x bar of cornflakes is 4.643. And the x bar of oat bran is 4.263. And so what we're wondering is, we can already tell that 4.643 is different from 4.263. This difference is equal to 0.3808. 0.3808. We already know that these are different from each other, right? What we wonder is, are they statistically significantly different? I can also give you the standard deviation of the difference, which is 0.4335. And I could give you the standard deviations or the standard errors of these as well. They all have values. I'm not sure if that's super duper important, but let's go ahead. If I need to fill those in for our discussion here, we can do that. So the calculated T statistic, I'm going to go ahead and fill this in. Let me get rid of this just because it's kind of in the way. So let's put that back. So square root of n. This is the x bar of the difference is 0.3808. Mu sub aught is always, or pretty much almost always, equal to 0. So remember, we're testing whether that difference is equal to 0. So that's the 0 right there. Standard deviation of the difference is 0.4335, 0.4335 divided by the square root of n, and in this case n is 12, so we want to take the square root of 12 there, and so what we end up with is t with 11 degrees of freedom is equal to 3.043. So there we have our t-value. That t-value is converted for that particular t distribution is converted into a p-value, and the p-value that we have for that is, let's see if I can find it really quickly here. The p-value is equal to 0.011, and so based on that particular p-value, we can already say reject the null. In terms of, so here we have the p-value version. We can also calculate a 95% confidence interval version, and hopefully you'll see also the similarities to the 95% confidence interval, which is x bar plus or minus, and this is x bar of the difference, plus or minus the t-value times standard deviation over square root of n. And in this case, x bar of the difference, remember, is 0.3808 plus or minus, and the T statistic for that, 95% confidence interval, I believe is 2.0 multiplied by the standard deviation of the difference, which is 0.4335, divided by the square root of 12. So what we end up with then is a confidence interval of 0.1054 to 0.6563. And one thing that I would like to point out is that when I do this, I include what's called the leading zeros. There are sometimes that people only include the decimal point, and what we've found is that that leads to people misinterpreting the number that they read. And so you'll see me include it. Technically, in some cases, it's not wrong to leave it off, but I personally believe that it is a better practice to include it, just because people see the decimal and they, in their minds, we know psychologically that people move it over, so then this number right here would turn into 1.054, which is a very different number. So I include the leading zero. The other important thing to notice here is that this 95% confidence interval does not include the test value that we're aiming for. In other words, 0 is not in between 0.1054 and 0.6563. 0 is not in that interval. And so on both of these cases, the p-value being less than 0.05 and the 95% confidence interval does not include 0, both of those agree that we should reject this null. The mean difference is equal to 0. We're going to say, no, I reject that. I believe that is incorrect. And in plain language, what we would say, it is unlikely for a sample with a mean sample difference of 0.3808 to have been randomly drawn from a population with a population mean difference equal to 0. And so that's how we would interpret that particular decision. If we were to write a conclusion, remember these are kind of like an APA format of the conclusion. On average, participants had a significantly lower LDL while eating oat bran, and here's my mean and standard error of the oat bran measurement, than while eating cornflakes, and here's my mean and standard error for cornflakes. Here we have the t-value is t-value with 11 degrees of freedom. Remember, degrees of freedom is n minus 1. and then the p-value that goes with that is 0.011. So that's how we would go through a paired samples t-test. I really hope that you look and see these kind of comparisons between the one sample t-test and the paired samples t-test. In terms of sample size, again, you're going to see a lot of similarities between these. The sample size here that we would need in order to detect a specific difference is equal to the standard deviation of that difference multiplied by the z, here also again 1.96, z of the confidence interval, z of power 0.84, and again exactly the same dynamic that we saw before. If the difference goes down, because this is in the denominator of this right hand side of the equation, if we want to detect a really small difference from the before and after, or from the cornflakes to the oat bran, then we're going to need a pretty big sample size. However, if we don't need to be able to, if that difference can be pretty large, then we're not going to need to have as large of a sample size in order to detect that, holding all the other things constant. The same exact kind of thing holds for the standard deviation. If my data is really spread out, then I'm gonna need a pretty, if I have a wide spread, I'm gonna need a much larger sample size in order to be able to detect a meaningful difference between them. If my difference is really narrow, then I won't need as big of a sample size in order to be able to detect that. These relationships right here are really easy to test on standard tests. They'll give you a scenario where blah blah blah, what happens if the standard deviation increases, what happens to the needed sample size in order to be able to detect such and such a difference, or what if you don't need to detect as small of a difference, what if the difference goes up, then your sample size goes down. Those are really important things to understand about sample size. Let me see if there's anything else I wanted to point out on this particular video. One of the things that's really important to remember, and you'll see this more as we get into the independent samples t-test and the one-way ANOVA, is that all of these tests that you're going to be learning in this first part, these tests of group means, and even including the next topic with correlation and regression, these are all the same test. They are just dressed up in a different name. So mathematically, behind the scenes, we're actually doing a lot of the math the same. So for example, in terms of data entry here, we really just included, whatever is that continuous variable for each person. Mathematically behind the scenes, remember we're comparing to some reference value. Here in our example, we were comparing to 170, 170, 170, 170, and instead of comparing like cornflakes to oat bran, we're comparing this weight to that and calculating some kind of difference. And so for each one, we have a different score. You don't see this in the dataset spreadsheet, but ultimately behind the scenes, we're really doing exactly the same thing mathematically. It's just with a one sample t-test, we're comparing to a reference standard. With a paired samples t-test, we're comparing two measurements for each person to their own reference or their own baseline. And so hopefully as we go through this, you'll start to see some similarities so that this all makes sense. That's really what we want, is for it to make sense. So that concludes our video on paired samples t-test. I hope that was helpful.